Um, Good afternoon, everyone. So today we will have the second APAC Ideas seminar that we will have today. The talk will be by Vandit Trivedi. I hope I pronounced the name correctly. Obtaining a biautomatic structure on a group via group action. Thank you, Vandit. You can begin.
Thanks, JV, for the introduction, and good afternoon, everyone. So yeah, as JV mentioned, the title of my talk today is Obtaining a Biautomatic Structure on a Group via a Group Action. This is, as we were discussing, it's part of the work that I've been doing for my master's thesis under the supervision of Adam Piggott at ANU. So before we start, I would like to thank him for the guidance and support over the last few months. So we'll get started. What we'll do today is firstly introduce automatic and biautomatic groups, provide some intuition and build up to what would be a formal definition. And then we'll look at ways to find or determine a biautomatic structure on a group. There are a few ways to do that. And we're going to look at one of those ways or methods in particular, especially through an example of a group acting on a simplicial complex. But before that, let's build up some intuition about automatic groups. So let's say I have a group G and some generating set A for that group. Given a group element, there are infinitely many ways I can spell a word over A to represent that group element. Because, for instance, if I take a generator and put next to it its inverse, and I can insert as many of those as I want, which means I have infinitely many representatives. So the question becomes, is there a nice way of representing group elements? Could we pick a favorite way, or as people say, a set of normal forms for each group element? One thing we could try is to find the shortest representative of a group element. And when we do that, there are a few questions that we might want to ask. We'll look instead of just words at the Cayley graph of a group with respect to some generating set. And corresponding to a word, that word traces out a path in the Cayley graph. And so we could ask, what do paths that correspond to shortest representatives, or geodesics, what do they look like for a given group? And another question we might want to look at is, do geodesics moving in roughly the same direction stay close to each other? That's something we'll make precise when we look at the definition of automatic groups. But before we do that, we're going to look at these questions in a few examples. So we'll start with the free group on two generators, F2. So I have two generators, X and Y, no relations between them. And I'll ask that question, how or what's the shortest way to spell a group element? Let's say we pick this point here. Let's use a different color. If we pick that point there, and this is my base point, the identity, that's where we're starting. It's quite obvious here that we just travel along the X and then go up a Y. That's the shortest representative. And another characteristic is that it's unique. That's the only shortest representative for that group element. Now let's say that I wanted to find a representative for a group element that's close to that point. Let's say that differs by a Y, the point right there. If I want to get there, I start along the path that we had before, and we just tack on an X at the end. So now you can see that I have two words, XY and XYX. And those two paths corresponding to those words stay close together. And in fact, not only do they stay close together, they're entirely coincident up to the last generator. So that's what we have in the free group. And it was fairly simple to think of an automatic structure on this. This would constitute an automatic structure on the free group. Now let's look at a slightly different example. Direct product of the infinite cyclic group with the cyclic group of order 2. The Cayley graph in this case looks like what you could describe as an infinite ladder. And again, I pick a base point. And let's say I want to find representatives for this element right here. There are a few different options here because I could go along the bottom and then go up, or I could go up first and then along the top. Or alternatively, I could go along the bottom for a bit, jump up, and then go along the top the rest of the way. And all three of those paths, as well as one more if I were to jump up at the second or at the next y, all three of those paths would be geodesics. They're all shortest representatives. So in this case, unlike our free group, which the Cayley graph was a tree, geodesics are not unique, but they do stay close to each other. If I take, for instance, the two geodesics corresponding to this point here, yes, they seem to go in different directions to start with, but then they're both traveling in the same direction and they stay within 2 units of each other. Now we have another example, the free abelian group on 2 generators. Again, there's a base point, and let's say I want to get to this point here, which I can again do in multiple ways. I could go along the bottom and then up, or I could go up and then along the top, or any staircase-like path within this square also constitutes a geodesic. So something like this is also a shortest representative. So again, obviously, like before, geodesics are not unique. Now the issue is that the geodesics don't actually stay close together, because if you look at just the light blue and the orange paths, they seem to be heading in quite different directions, at least for the first few units along the path. And so those paths don't stay together. And if you think about group elements that are even further out, those squares will be bigger and bigger, and those paths will get further and further apart before they come back together. So geodesics aren't unique, and neither do they stay close to each other. But what we can do instead is, instead of taking all geodesics or all shortest representatives, I can pick one particular one. I could say, for instance, that I'm only going to look at paths that go along in the x direction first and then go in the y direction. So you go left first or right first, and then up or down to get to where you need. And what I'm doing is, instead of picking all geodesics, I'm picking one representative, and those geodesics would in fact stay close together. So that's some intuition behind automatic groups, which actually brings us to a definition. So this is actually a definition of an automatic structure on a group. So if I have a group G along with a generating set A and a language over A, by a language, I just mean strings in the generators A, or words over A. And this language satisfies certain criteria. Firstly, we'd obviously want every group element to have at least one representative in the language that we've chosen. Secondly, the language is regular, which is something I'm not going to go into, but what it means is that it's recognized by a machine called a finite state automaton. And thirdly, this is what we've been discussing in the last few slides, the language L, fellow travels. Paths that end close together stay close together throughout. So let's make this notion a bit more precise. I have here again a base point, the identity E, and then I have two paths corresponding to words W1 and W2. And those two paths end up close together. They differ by a generator X in my generating set A. And what we mean by these two paths fellow traveling is that if I take a step along the path corresponding to W1 and a step along the path corresponding to W2, mark those vertices and calculate the distance between them, and I keep going, take another step along W1 and another step along W2, and so on, that distance between the first I steps, or the prefix of length I, is bounded by some constant K. And so that's what we mean by paths fellow traveling or staying close together. That's the notion that we were discussing in the previous few slides. That's a biautomatic structure. Sorry, that's an automatic structure. A biautomatic structure, there are various ways to characterize this, but one way is, if I have an automatic structure AL on a group G, that's also biautomatic if the language L inverse, it's just a set of inverses of strings in L, if that is also an automatic structure. And an automatic group is just a group that has an automatic structure. So this is something I had in the abstract for my talk. There's an open problem. we know certain groups that are automatic, but we don't know whether every automatic group is also biautomatic. And what complicates this is that not every automatic structure is biautomatic. In other words, I can find a language along with a generating set that's automatic, but is not biautomatic. And there may be multiple automatic structures on a group. And so that's one of the things that makes this problem a bit challenging. But that's all I'm going to say about that open problem. What I wanted to get at for the rest of the talk is how do we actually determine a biautomatic structure for various groups. We've seen what we could say is a direct approach. We just look at a Cayley graph and it might be obvious as to what paths we can choose that form a regular language of normal forms that fellow travels, as it was in our examples that we saw. But other groups, it might be more difficult. And so we might have to do this in what I describe as an indirect way, where we look at the action of a group on some geometric object. And these are two theorems that I've looked at during my project. One is by Niblo and Reeves from 1998. If I have a group acting in certain ways, effectively, cellularly, properly discontinuously, and co-compactly on a simply connected, non-positively curved cube complex, which means that the cube complex is cat 0, then the group G is biautomatic. Not only does this theorem tell us that G is biautomatic, it actually gives us a way to find that biautomatic structure. And another one is by Januszkiewicz and Swiatkowski from 2006, a group acting simplicially, properly discontinuously, and co-compactly on a systolic simplicial complex X, then G is biautomatic. And this theorem also gives us a way to find a biautomatic structure on G. So before we go further, I just wanted to compare a few things between these theorems. We have a few properties of the group action that correspond. Cellular means that the action sends vertices to vertices, edges to edges, squares to squares, and so on. Simplicial means that the action sends vertices to vertices, edges to edges, triangles to triangles, and so on. We also have co-compact in both, as well as properly discontinuously. Co-compact just means that the quotient space X by G is compact. So we're going to look at the second of these, group acting on a simplicial complex. And this is a very vague overview of how one would find an automatic structure on a group. So we have a simplicial complex X, which consists of vertices, edges, triangles, tetrahedra, and so on. And we construct the barycentric subdivision X prime, which I'm going to get to in the example. We find the quotient of that space by the action of G, pick a fundamental domain. And this is how we get our automatic structure. Edges are going to give us the generating set A, and what we call directed geodesics, which are sequences of simplices that are optimal in some sense, that's going to give us a language that maps onto our group G. And the key is, as with cube complexes, in simplicial complexes as well, directed geodesics between vertices are unique. And this is what makes things work. This is what allows us to obtain a biautomatic structure on a group. So let's spend the rest of the time looking at an example. I have a group here, which is the semi-direct product of the infinite dihedral group with Z2. And it has this presentation, 3 generators, all of which are involutions or self-inverse. And I also have these 2 relations that come from the semi-direct product. Since each of the generators is an involution, we don't need to write inverses. A is equal to its inverse. I'm just going to write A for A inverse. And we're going to look at the action of this group G on this simplicial complex in orange. So how does G act on X? I've drawn in a few dashed lines. Since each of the generators are of order 2, we can think of them as being reflections or 180-degree rotations. So we're going to think of A as being reflection in the line corresponding to A. We'll think of B as being reflection in the line corresponding to B. And we'll think of C as being a 180-degree rotation about this point, which a rotation can also be thought of as a product of reflections. So you can also think of that as being a reflection in the vertical line through to that point and a reflection in the horizontal line. through that point. So once we've done that, I said we construct a barycentric subdivision of this complex. So every edge I divide into two, mark a vertex at the midpoint, connect that edge to the opposite vertex of the triangle, and do this for every edge that I have in my complex. And where those edges meet at the centroid of the triangle, that also becomes a vertex in the subdivision. So I've drawn that in, and now we're going to look at how this group acts on vertices in this complex. So let's say that we start with this vertex here, which was blue, and I've just written over it in, or drawn over it in a lighter blue. Well, A is a reflection in that line, so it does nothing in this to this point. B is a reflection in this line, and so that's going to take this point out to here. And then C is going to rotate this about this point, so that will take this reference point down to here. And then once I get down to here, I can take this point wherever I want along the bottom, and I can also take this point along the top wherever I want. And so that forms one orbit of vertices in this complex. And the same thing you could repeat for the other vertices that I've marked. I've already colored them in. So if you look at the midpoints of the edges at the bottom that are marked in red, they form an orbit along with the vertices at the top. The vertices along edges that connect the top to the bottom also form an orbit, as do the centroids of the triangle. So there are 4 orbits of vertices in this case. And what we're going to do is we'll label those vertices according to the orbit in which they lie. So I've labeled them P, Q, R, and S with some subscript, positive subscripts going to the right, negative indices to the left. And I've just picked this area here where the vertices are labeled 0. That forms what we call a fundamental domain, which I won't go into today. So once we've labeled these vertices, we can ask, what do directed geodesics between vertices look like? So for instance, if I have this vertex P0 and I want to get to another vertex, let's say P2, what's an optimal way of getting there using a sequence of simplices? In this case, the directed geodesic is just the vertex P0 followed by the vertex P2, and my path corresponding to that would be the edge connecting them. Let's say I wanted to go out further to P4, what would my directed geodesic look like in this case? Well, it's also fairly simple because they lie along the same straight line. And the sequence of simplices is just this vertex P0, the vertex P2, and the vertex P4. And the path that is induced by that is just the line or the sequence of edges along that top row. How about if I want to get down to, say, P1? Again, this is fairly simple because P0 and P1 are connected by an edge in my original simplicial complex. So I just travel down here, and my sequence of simplices is the vertex P0 followed by the vertex P1. Where it gets a bit more interesting is if I want to go further out as well as down to the bottom. Let's say I want to get to P3. What would my sequence of simplices look like? In this case, the sequence of simplices is P0, this edge P1, P2, and then the vertex P3. And what this does is it induces a path where I take all the edges in the subdivision that lie within that sequence of simplices, and that becomes my directed geodesic from P0 to P3. And you could ask the same thing, what happens if you go further out? Let's say I went to P5. Well, it's quite similar. P0, cross this edge P1, P2, and then the vertex P3, followed by the vertex P5. Another thing we could do possibly here is instead of crossing from the top to the bottom at the start, we could instead go along the top, cross this edge, and then go to P5. in terms of length, they both have the same length. They're both a sequence of 4 simplices. But it turns out, and again, I won't go into this because of time, that it's actually the first sequence of simplices that forms the directed geodesic in this case. And so the idea is that if I want to go from the top row of vertices to the bottom, we have to cross the edges first, and then we travel along the bottom as far as we need. So that's what geodesics in this directed geodesics between vertices look like. All right. So once we've done that, what we can do is label each vertex with a set of group elements that take a chosen representative to that vertex. So if I go back one slide, I had here my base point, P0. So I can look at all the vertices labeled P and find which group elements take P0 to my chosen vertex. And that's exactly what we've done in these tables. So I formed what group elements take my reference vertex to any vertex in the same order. And there are 2 group elements that do that in this case for every vertex. All right. So now what we can do is use these labels on the vertices to come up with an alphabet that we can use as our generating set. So what we do is every edge in my subdivision, X prime, is given a multi-labeling, which is just defined as this. If the multi-labeling between 2 vertices is the set of labels for one, the inverse of that, times all the elements that are the set of labels for the other vertex. And if I do that, I've done this just for a few vertices that would lie in the fundamental domain. And these are the group elements, or these are the words that I get. And this is what constitutes the distinct words in this table are what constitute the generating set for my bioautomatic structure. So we have here A, C, AC, which I'll relabel X, CA, which I'll relabel Y, and ACA, which I'll label Z. A couple of features about this set is that it will always be inverse closed, which you can see because I have AC and CA. ACA is of order 2 as well. The other thing you'll notice is that there are no B's in this set. If we think back to our group presentation, we had this relation. What this means is any occurrence of B, you can replace with the string CAC. And so B's are not required for our alphabet. And the reason why I don't have B's rather than I don't have A's is to do with how I had picked the edges in this table. If I picked a different set of edges, I would get B's and C's rather than A's and C's. So that's how we obtain the generating set. And the language L is obtained by basically looking at directed geodesics, and each directed geodesic, as we saw in here, induces a sequence or a path, a sequence of edges. And you can think about the multi-labeling for each of these edges, and that is what constitutes the biautomatic structure. So I think about the labels for each vertex along that sequence of edges. I look at the multi-labeling, and all possible combinations of that is what gives us an automatic structure on the group. So you can sort of get an idea here that it's going to get pretty computationally intensive because I'm going to have to enumerate a lot of possibilities. So that isn't something that I'm going to do here today, but that is something that you can do now for your favorite group. So with that, that's all I had to say today. And are there any questions?
I'll ask one question. You stated an open problem earlier that was to determine whether every automatic group is biautomatic.
Yeah.
Do you know if this has been solved for certain classes of groups already?
Yes, it has. I know that it's been solved for a few classes of groups. In fact, I saw a paper, I think, from last year, which had a certain class of Coxeter groups were proven to be biautomatic. So it has been solved for certain classes of groups, but not in general. Yeah. In fact, all of the structures that we described in these elementary examples, all of them are also biautomatic. But where things go wrong is, for instance, if I have a path in this here, where I do this, that's automatic. But then if I trace this square as many times as I want, that isn't going much further away from the path that I started with. So that still remains automatic. But the problem comes when you try to reverse that, because what's going to happen is that you're going to go around in circles around that square many times, while the other path might have already gone quite far, and they end up being quite far apart. So that's why not every automatic structure is biautomatic, but you can, in these examples we've chosen geodesics so that they were.
Can I just maybe further specify my question? Do you know if there's examples of classes of groups where not every group in that class is biautomatic, but this problem has been solved for that class of groups?
Where it's known that not every group is biautomatic, or
yeah, like say we have a class of groups,
yeah,
and not every group in this class is biautomatic, but it holds for this class of groups that automatic implies biautomatic.
Okay.
Maybe that's too specific of a question.
I can't think of any examples right now. Yeah, that's an interesting one.
That's fine. And when you defined an automatic structure earlier in the here, does that constant k depend on the distance between the endpoints?
Well, so when we define fellow traveling, we're essentially defining it to mean paths that end distance one, or at distance at most one apart. So yes, it would. If I pick paths that were further apart, then this constant k that end further apart, then that constant k wouldn't work. But in the definition of fellow travelers, we basically we only look at paths that end within a generator of each other.
Right.
And so that constant is fixed for a given automatic structure.
Okay. Thanks for the talk.
Are there any other questions from the audience?
I just have one question. Is there like some intuition for me behind like why it's called a language, L?
Yeah, so it's essentially when we're thinking of these group elements or the paths, we're essentially thinking of, let's say I have, actually let's do this for an example. This group here, I have two generators, X and Y. The reason we call it a language is, for instance, this point here is represented by the word XY, but it's also represented by the word XY, X, and X inverse. And so these we can think of as being words, and everything strings over my generating set form, that's A star means all possible strings, and L is just a subset of all possible strings. So it's thinking about my generating set as letters and L as a sets of words over those letters.
Okay. All right. Okay. So you're trying to effectively get rid of like trivial representations of a given element in the group.
Yeah, that's right. That could be one way to come up with an automatic structure. That's what we did in this case. Yeah.
Okay. All right. Thank you.
Any other questions? I guess with it, we will then finish the talk for today. Let's thank again Vandit for the talk. Thank you very much. And